Hey, Mr. Maestas here, and today in this video I am going to go over composite functions. So we will look at a few examples and we'll talk about the composite function, how to find a composite function, and also how to find the domain of a composite function. And then we will also look at a couple of practice problems. So I'll go through two examples and a couple of practice problems. So basically, the idea is sometimes we write it in this notation. It's sometimes we say fog, but really it's f with a little circle. F of g of x. So what we're doing is we're taking a function and we're putting it into another function. Sometimes we write it as f of g of x like this, and I prefer this way because it makes more sense on that we're taking that function g and we're plugging it into to f. Okay, so we've got a function in a function. That's why it's called a composite. So let's take a look at the first example here. F of x equals x squared plus 1 and g of x equals 2x plus 1. And just so we can give it a little color here, I'll go ahead and make g of x 2x. I'll make 2x plus 1 blue. So we can see that we're going to be plugging it into the function, like which function's going into which one. Okay, so we want f of g of 1. So what this is going to look like, and I'll just rewrite it as f of g of 1, like this. And we're going to take 1, and we're going to plug it in to the g function because we want g of 1. So we're going to have, this is going to be f of g of 1, so we're going to plug in 1 here. We're going to get 2 times 1, which is 2, plus 1 is 3. So g of 1 is 3. And then we're going to do f of 3. So then we're going to take this and we're going to plug it in to our f function. So we're going to have 3 squared plus 1, which is 10. And that's going to be f of g of 1. So let's do the other thing. Let's do g of f of 3. Alright, so we have g of f of 3, like this. Alright, so we're going to take 3 and plug it into our f function. So we're going to have 10. We just figured that out here, right? F of 3 is 10. So we're going to have g of 10 because 10 was our f of 3. And then we're going to plug in 10 into our g function, and we're going to get 2 times 10 plus 1 is 21. All right? So that's f of g, and then that's g of f. Okay? That's if we're plugging in a number, but what if we want to plug in just our variable? What if we want to do the functions f of x and g of x? All right, so let's take a look at f of g of x. So what we're going to do is we're going to plug in, and I'll write it as this other form, f of g of x, like that. And we're going to take the g function and plug it into our f function. So we're going to have f of g of x is going to be, everywhere we see an x here, we're going to plug in all of g. Alright, so 2x plus 1, and that's squared, plus 1. Okay, and we got that because we took all of g here, and we plugged it in right here for x. Okay? So let's go ahead and we're going to go ahead and expand this out here. So 2x plus 1 squared. Right? We have to FOIL that one out. I've been foiled. 4x squared plus 4x plus 1 plus 1. And we get 4x squared plus 4x plus 2. And this would be f of g of x. Okay? So, I'll be right back and we'll do another example, okay? So, come right back. Okay, first another example here. So, one thing I want to mention though is that for this example we're going to take a look at the domain of f of g of x. And I want to let you know here that there's really only one basic rule that you need to know for domain of composite functions, and that is the domain of f and g of x is restricted by both f of g of x and g of x, or the inside function, whatever function that we plugged in, also is going to be a restriction. And so we'll take a look here, and we'll need to do both the domain if we have a domain restriction for f of g, and we have to check to see if that domain is restricted by g also. Remember that all polynomials have a domain of all real numbers. So if g is a polynomial of all real numbers, then you know there's really no restriction on that, so it's whatever comes out to f of g of x. We'll take a look at this example, and then we'll have a couple of practice problems, and we'll take a look at those domains too. So you should have 3 after this video of examples of the domain of composite functions. Okay, not restricted by the outside function though. Let's take a look. So let's first do f of g of 2. So we're going to plug in 2 in here for the g function, and we're going to get 1 over 2, which is 1/2. So we have f of 1/2, okay, because g of 2 was equal to 1/2 when I plugged 2 in for my g function. Then I'm going to plug in 1/2 into my f function. I'm going to get 1/2 over 1/2 plus 2. Oh my goodness! I've got fractions within fractions. So let's take care of that. Easiest way to do that is to get a common denominator. Well, I think easiest way to do that is to get a common denominator in the bottom. So we're going to change this 2 to 4 over 2, right? Because 4 over 2 is 2. Common denominator, so we got 5/2. And 1/2 divided by 5/2 is 1/5. Alright, so there's my answer. Now how did I do that? It's like fraction magic. You can take 1/2, since you're dividing by 5/2, you can multiply by the reciprocal, so 2 over 5, and you'll get 1/5. Or the easy way to do is just cancel out the denominator 2's and get 1 over 5. Okay, so we've got 1/5. So let's take a look at f of g of x, and then we'll look at this one. We'll look at the composite domain. So f of g of x is going to be f of 1 over x. Okay, so all I'm going to do is I'm taking g of x and I'm just replacing all my x values in f for 1 over x. So I'm going to get 1 over x over 1 over x plus 2. So now again, in order to deal with this fraction within a fraction, I'll need a common denominator, which is x. So x over x, right? So if we cancel these x's out, I'd have just 1 over x plus 2. So I multiply the top and the bottom by x. Alright, so I'm going to get 1 over x over 1 plus 2x over x. And then just as with these 2's simplified here, these x's are going to also simplify out. And we're going to have 1 over 1 plus 2x. Alright, and there is my f of g of x. Now we need to check the domain. So let's take a look at the domain. The domain of this, we're just going to take the domain of f of g of x, what we have here. And the domain, remember, is the denominator cannot equal 0. So the domain right now, we know that 1 plus 2x cannot be 0. So we're going to solve that for x, and we're going to say x cannot be negative 1/2. So we cannot have x equal negative 1/2, because if we did, this right here would be 0. Or the bottom right here would be 0, and we would, cease to exist, I guess. So we can't have the denominator with 0. Now, the thing is, though, is that there was a domain restriction here for g, and g was the function that we plugged in. So here, if you remember, 1 over x, the denominator cannot be equal to 0, so there we cannot have x equal to 0. So since the g function had a restriction, x cannot be 0, we also have to add it to the domain restriction of my composite function. So not only is x not going to be equal to negative 1/2, but x is also not going to be equal to 0. Again, because g had that restriction. Now, if I wanted to write this in interval notation, that would look like this: negative infinity to negative 1/2, then negative 1/2 to 0, then 0 to infinity, right? Because it's basically all real numbers except for those two. Okay, so I'll be back with one more. Actually, I'll be back with 2 practice problems. Well, 1 practice problem with a bunch of things in there. Okay, so I'll be back. Okay. Okay, practice problem. So I will stand, oh, I better stand out of your way so you can copy the practice problem down. Okay, so one of my students does, she does like this. Okay, so copy that down and then I'll go over it. So pause it now. Now let's go over it. Okay, so hopefully you had an opportunity to do this problem here, and we've got f of x equals x squared minus 4, g of x equals square root of x plus 1. Hopefully you didn't freak out at the square root, and I know it's a little bit different, but the process is the same nonetheless. So let's go ahead and plug in. Now this is f of g of 3, right? I don't think that's going to show up all too well on our video here. So let's get orange. We're going to plug in 3 into our g function, and we're going to get square root of 3 plus 1. 3 plus 1 is 4. Square root of 4 is 2. So we got f of 2. 2 in here. 2 squared is 4. 4 minus 4 is 0. So we got 0 for our answer. Not bad. Okay, g of f of 2. We're going to plug in 2 for our f function. 2 squared is 4. 4 minus 4 is 0. So we're looking at g of 0. Plug in 0 in here. 0 plus 1 is 1. Square root of 1 is 1. Okay, so we got 1. Alright, hopefully you got those right. Now let's take a look at f of g of x here and find its domain. So we're going to take, this is f of g of x. Now you might want to write it this way. It just makes a little bit more sense, right? So f of square root of x plus 1. Now I like to write it in here because later on when you get to calculus and you get to do some other things, you're going to do something like finding f of x plus h, or f of a plus h, or a lot of little composite functions that you'll have to do. So I like to write it this way just to kind of get you used to that. Square root of x plus 1 is going to go in here for x in our f function. So we're going to have f of g of x is going to be the square root of x plus 1 squared minus 4. Well, what's the square root squared? Square root squared just kind of cancel each other out, right? And it has to do with the powers and stuff, but for now, the square root squared is just whatever's inside, x plus 1. Okay, don't confuse that, by the way. Don't confuse that with the square rooted. So the square root of x squared. That's something different, which we'll get to in a little bit. But not on this video, but we'll get to some other time. So we get x minus 3. Okay? Now x minus 3 is a line. So the domain, what's the domain of a line? Well, the domain of a line is all real numbers. It's a polynomial. However, remember that this composite function is bounded, it is restricted by our g function. And our g function was a square root, and we remember from our domain video that a square root cannot be negative. So our domain of this here was that x plus 1 must be greater than or equal to 0, giving us that x is greater than or equal to negative 1. So, since our composite function must be restricted by the inside, which was g of x, our domain, even though this looks like a line, our domain is going to be x greater than or equal to negative 1, which I'm going to write in interval notation as negative 1 to infinity. Okay? Alright folks, composite functions, see you later.